Hello, I'm Hugh Manfield and welcome back to the Fluid Space Theory videos. Now today I'm going to do a little summary of what we've learned in the first core 10 video lectures and give a little history about how and why I came up with all of this. So for starters, what does fluid space theory do? Well, it replicates Newton's gravitational theory and it replicates Einstein's general relativity theory for gravitational fields. Now, why is this important? Is because any new theory has to replicate the results of the earlier successful theories, and then it has to do something more. So what does fluid space theory do this more? Well, it reveals that there's a contraction field around normal matter. This is a new property of matter that is not formally understood. And this contraction field replicates the behavior of dark matter. So fluid space theory is more complete in replicating observations of our universe. Fluid space theory also reveals an expansion field around antimatter. And what this does is this restores the matter-antimatter balance, which experiments have shown ought to be there. There really should be an exact parity. So instead of looking for some tiny discrepancy in the production of antimatter and matter, which we don't have any evidence for, now we can say we do have evidence for an exact match. So the space between galaxies and the voids out in the cosmos are probably filled with antihydrogen as a gas that is dispersed by its expansion field. Fluid space theory provides a new model for black holes, not with a singularity, but black holes that contain a space-time discontinuity. And fluid space theory also reveals a cosmos that expands without getting bigger. It expands without the distances between galaxies increasing. What's going on is the vacuum energy of the universe is slowly declining. That means that the length contraction and the time dilation is going to go away. And when we look out into the distance, we're going to see galaxies in the distance as they were in an earlier stage when they were more length contracted and more time dilated. Therefore, they will appear redshifted and increasingly so with distance. And this type of cosmic expansion doesn't need dark matter or dark energy. Some other things I've shown in the first 10 lectures is how gravity is an acceleration field in space-time, how Newton's laws relate to space, how sync flow with relativity creates a gravitational field, and this reveals the true nature of matter, that it is energy fields around tiny discontinuities in space-time. And I've talked about the old news aberration and why it must always be accounted for, and how expanding or contracting space-time ought to affect an orbit. So if you haven't watched all of the 10 core videos, I suggest that you do. And if something's not clear, you ought to watch them again. And I'm not saying this to get more views, although more views would be nice. I'm saying it because these ideas take a little while to get used to. This is a new way of thinking, a way that physicists don't normally think. And it takes a little while before it all starts to gel and make sense. But once you understand it, it is a much better approach, a much more complete approach, and a lot easier to understand. So why did I do this? Did I set out planning to discover properties of matter and antimatter that nobody knew? Did I set out to solve the mysteries of dark matter? No. All I wanted to do was learn a little bit more about physics. I had taken a few elective physics courses in engineering school, and I was a bit disappointed because in those courses they only touched on the very basic material, and most of the book that I bought wasn't even used. You know, the advanced chapters on relativity, electromagnetic theory, and quantum theory, they didn't even get to. So I was a bit disappointed. And about 10 years after graduating, I was commuting to a job, and I had about 2 hours a day with nothing to do. So I decided I was going to start reading about physics and learning those subjects that I had missed out on earlier. So I did it basically out of my own curiosity. And I also wanted to work out something that had been bothering me since I was a teenager. This was back in the 70s. We were sending men to the moon. Everyone was excited about the space race. There was a Skylab and lots of things were going on back then. And one day while throwing a football around, I guess I might have been frustrated about how far I could throw it. And I was thinking, well, if I was out in space, I could throw this ball as far as I want because it would continue in a straight line at a constant speed forever. And then I thought, yeah, but if I did that, I'd never get the ball back. And what I would need is a rocket-powered football field so that I could turn on the rockets and the field would catch up to the ball and you'd see the ball fall back in an arc just like it was in a gravity field. And then I was thinking, well, you know what? What if we brought that rocket-powered football field down to Earth? When I throw the ball, it must be that the field I'm standing on is accelerating upward relative to the space of the ball, and that's what brings the ball down to the Earth. Actually, I thought it was kind of a smart idea. And then after thinking about it a little bit more, I realized that the Earth is round, and that would mean that the Earth is sucking up space from all directions, which seemed kind of silly. But the idea still bothered me, so I started working on it. And what I've learned about relativity is, like in special relativity, or actually even in general relativity, you always have two different points of view. Now, in a field, like a gravitational field, you'll have the outside point of view, someone greatly removed from the system, and you'll have someone with the inside point of view who might be standing on the surface of the planet. And those two points of view are different, but using the correct theory, you can reconcile those 2 points of view to match the same set of equations. Well, that's what I did with the fluid space inflow theory. I reconciled the inside and the outside point of view and came up with something that I thought was pretty interesting. It revealed that matter isn't a bunch of tiny particles moving around in a void. It's a bunch of tiny voids moving around within fields in space-time. So it's kind of an inside-out approach to the normal view of what matter is. And I thought this is a fairly important idea. And this idea comes from envisioning a black hole without a singularity, which, by the way, these singularities cause a lot of problems in physics. Instead, it has a tangency and it forms around a space-time discontinuity. And this construction of a black hole actually yields something that will ring or vibrate like a bell, and if it's a small particle, it will lead directly into quantum behavior, and I'll be covering that in a future video. And fluid space theory also revealed to me a cosmos that can expand without the galaxies getting farther apart, which makes things a whole lot easier. And it expands by the loss of vacuum energy, the gradual loss of vacuum energy over time, which is a lot more natural process. Once I'd gotten this far into the theory and I'd realized what dark matter is and the new properties that we would see in antimatter, all of the mysteries of physics started to fall into place for me. And I thought I really ought to share this because I think it may be important. This could be the theory that takes humanity to the stars. Who knows? It's very difficult in today's world to raise a new theory and get any attention. There are tons and tons of theories out there, and not everyone does their homework and makes sure that what they're promoting actually works. And I don't know if you've tried to contact a physics department at a local university and tell them that you have a new theory of the universe. If you have, you'll see that they're not exactly welcoming of new ideas from people outside of physics. So if you agree with me and if you think these ideas are important, what could really help is getting the word out. Likes and shares. Share it with someone in physics that you know. point them to these videos and say, you know, this guy makes sense to me, a lot more sense than you make. Why don't you listen to him? Now, some other things that I'd like to see done with fluid space theory is we could use computational fluid dynamics to model elementary particles. You could actually create an inflow field in CFD and see how it behaves as a particle. There are ways we might be able to test the Hubble expansion model and see if the fluid space theory model actually matches observations better. I'm going to show you the power of higher dimensions. I'll be talking about how fluid space theory actually folds seamlessly into quantum theory rather than being in conflict with it the way general relativity is. Now, this is kind of exciting to me. So once you understand a phenomenon more completely, you have a better chance of being in control of that. Just look at what happened with Faraday's law. Everybody saw lightning and they knew about magnetism, but nobody knew what to do with it. Well, Faraday came up with Faraday's law. It's the law that describes electromotive force. And since then, we have tons and tons of electrical devices, and it's done amazing things for the world. Well, understanding gravity could lead to gravity mechanical devices. Now, I'm not saying I know how to do that right now, but when you understand a phenomenon more completely, there's a better chance of controlling it. But what I do know now is that there are some places we could look for natural occurrences of anti-gravity. One place that I've already shown is the expansion field around antimatter in the cosmos at large. It would create repulsive dark matter field, basically preventing antimatter from clumping together into stars and galaxies. And this is like one example of outward gravity or repulsive gravity. But there could be some others, and I'll be covering those in a future video. And then finally, I think understanding matter as fields around a space-time discontinuity could lead to a better understanding of how electric charge attaches to matter. Down at the quark level, for every piece of matter with mass, it carries some kind of electric charge. Somewhere down at that level, there's an attachment between charge and mass. And I think we could understand that better. But the thing is, I did all of this on my own with nothing more than an iPad and a Windows PC. What I've discovered with fluid space theory is really the low-hanging fruit. It's the easy stuff. But I'm sure there's a lot more out there to be discovered if only someone would pick up the ball and start working with it. So I'm open to anyone who wants to join in and start working on fluid space theory. I'm convinced that the first major institution that begins to investigate fluid space theory will quickly be running circles around everybody else, making announcements and discoveries at a high pace. And everyone else will be scrambling to put together their own fluid space theory departments and trying to catch up. So what you can do to help with this, like I said before, likes and shares and get the word out. So until next time, I'm Hugh Manfield.